You've probably heard of the term entropy before in a science class, but let's talk about how it relates to computer science. So generally speaking, in all contexts, entropy is simply the measure of disorder or non-uniformity of a system. So for example, in physics, entropy could measure the disorder of molecules. In computer science, we're going to be talking about the disorder of information. So Shannon entropy is the expected value or average of the information contained in some data. So imagine that you have a coin that you're flipping. So a coin has two sides, heads or tails. A single flip of this coin, if it's a heads, that means that, oh, I got a heads. I got a heads out of these two possibilities, heads or tails. So if you think about it, there's only two possibilities that I could have gotten. So if it only has two possibilities, this gives me 1 bit of information. Right? The single flip of a fair coin would only give me 1 bit of information. There's two possible scenarios, and I now know which of those two scenarios I got. That's 1 bit of information to represent. However, what if I was dealing with a biased coin? So let's say I had a biased coin in which both sides were heads. If I were to flip this coin, I would always get heads. So any new flip of this coin doesn't give me any information whatsoever. So the flip of a biased coin that was guaranteed to flip heads would give me 0 bits of information. I already knew everything before I even flipped the coin. In general, if there's n possible outcomes, then a single event, so a single sampling, gives me ceiling of log base 2 of n bits of information. So when there were 2 possible outcomes, I got log base 2 of 2, which is 1 bit of information. This is bits of information. When I had a biased coin that only had 1 possible outcome, log base 2 of 1 is 0. That gave me 0 bits of information. There's an important relationship between the uniformity of data and the information contained within that data. So first, let's define uniformity. So uniformity is the lack of variation of symbols in a given message. So for example, let's say that I have the sequence A. This sequence is not very variable. It lacks variation, therefore it is highly uniform. This is a uniform message. On the other hand, the message ACGT, this is a highly variable message. Both messages are over the alphabet ACGT, but one is uniform, one is highly variable. So generally speaking, the more uniform the data, the less entropy. And if there's less entropy, that means that there's less information. So there's less information stored in this message than there is in this message. And if you think about it, we can kind of prove this to ourselves using basic computer science. So if we were to represent each letter as a byte, this string would take 8 bytes, versus this string would also take 8 bytes. But if I knew in advance that the only letter I was going to see was A, I could theoretically represent this string as the number 8, which I could represent A using only 4 bits, right? It would be 1, 0, 0, 0. So I only need 4 bits to actually represent this string. Versus this string, there's no simple way that I would represent it. I could probably do better than 8 bytes. So for example, I could use 2 bits to encode each of these letters. So if I used 2 bits for each letter, that would be 16 bits total, which would be 2 bytes. But still, 2 bytes to potentially represent this versus less than 1 byte to represent this. You'll see that the more uniform our data look, the less entropy there is, and therefore the less information.